Hello there, students. In this video, we're going to cover a tool that is used in physics mainly in the context of vector cross products, and that is the right-hand rule. A vector cross product is written like this. Here we have a cross product between vector A and vector B, and the result is a new vector, vector C. Geometrically, this cross product looks something like this. We know that vector C must be perpendicular to both vectors A and B, and that if we switch the order of vectors A and B in our product, we pick up a negative sign in our resulting vector. So what is this right-hand rule, and how does it help us with this cross product? If we position the index and middle finger like so, letting our index finger point along the first vector in the product, vector A, and our middle finger along the second vector in the product, vector B, then vector C is in the direction our thumb is pointing. Our index finger always points along the first vector listed in the cross product, and our middle finger always points to the second vector in the product. So now that we know what the right-hand rule is, and how it is used for cross products, how does this help us in physics? Well, cross products show up all over physics. Cross products are also used to define all of our coordinate systems too. Let's see how. We should be familiar with one of the most common coordinate systems, the Cartesian coordinate system with x, y, and z axes. The unit vectors that define these axes or coordinate directions are related in a very specific way, and that is defined by a cross product. And once you know it, you'll never draw a Cartesian coordinate system wrong again. This cross product is between the unit vectors that make up the three dimensions of the Cartesian coordinate space, x hat, y hat, and z hat. It tells us that if we choose a direction for x hat and then a perpendicular direction for y hat, the direction for z hat can only be in one direction. Let's use our new right-hand rule to see that the z-axis must be in this direction. We can also see that once we've got the coordinate system drawn correctly, we can confirm these other cross-product relationships for the Cartesian coordinate system. I encourage you to take a moment and confirm all of them. We can move on to the other two coordinate systems in physics to see what those relationships look like. Let's take a look at the cylindrical coordinate system next, which has unit vectors rho hat, phi hat, and z hat. It is defined by the cross product rho hat cross phi hat equals z hat. Let's see what this looks like. We start with a Cartesian coordinate system with the z-axis pointing up. If we choose a point on this cylinder and measure the angle phi going from the positive x-axis to the positive y-axis, the unit vector phi hat is in the direction of increasing phi like this. Then, z hat is the same as before, it just points in the positive z direction. Rho hat is our radial direction, and it points in the direction of increasing radius. As we move away from the origin, parallel to the xy plane, the radius of our cylinder increases. So we draw the unit vector rho hat like this, pointing away from the origin, but parallel to the xy plane, or perpendicular to the surface of the cylinder, whichever helps you remember. Note that phi hat is also parallel to the xy plane. Phi hat and rho hat are both parallel to the xy plane because they have no vector components in the z direction. This is because moving in the z direction doesn't increase the angle phi or the cylinder's radius rho. With all of the unit vectors in this coordinate system labeled, you can now take a moment to confirm all of the related cross products. The last common coordinate system in physics is the spherical coordinate system. This system is defined by r hat cross theta hat equals phi hat. We start with a Cartesian system again, we drop a sphere into the system and pick a point on the surface. Once again, we measure the angle phi, known as the azimuthal angle, from the positive x-axis towards the positive y-axis, and the unit vector phi hat is in the direction of increasing phi. The polar angle theta is measured from the positive z-axis and increases as it spans to the negative z-axis. Therefore, theta hat, which points in the direction of increasing theta, looks like this at our point. r hat points in the direction of increasing radius again, which is radially away from the origin, here. Notice that in this coordinate system, r hat is not necessarily parallel to the xy plane like it was for ρ hat in the cylindrical system. With all of this established, we can now use the right-hand rule to confirm all of the other relationships. There is one special case where a right-hand rule doesn't look quite like what we've already discussed. This one was used by Oersted in the context of current-carrying wires and magnetic fields. If you have a current-carrying wire, and you point your thumb along the wire in the direction of the current, and wrap your fingers around the wire, the B field will be curling in the direction of your wrapped fingers, like this. This is a result of the Biot-Savart equation. If we take a look at a single point in space near the wire, the velocity vector of an electron in the wire is going with the current, and the position vector from the electron to the point in space is vector r. Since vectors aren't attached to physical objects in space, we can move them to our test point so that we can better understand what we're calculating as the B field at that point. Following our right-hand rule that we've learned, we see the B field is pointing out of the page towards us, like this. So, at this one point in space, the B field is in this direction, but as we rotate this point around the wire, we see that the vector r changes, and so too does the B field vector, from which we see this curling trajectory. I hope this helps you understand how we use the right-hand rule in physics a little better. Thanks for watching and learning about physics. If you have any questions, please leave a comment on the video or head to my Facebook page in the video description.